Good morning. Welcome to my stream. Hello, Londo. How are you? Thanks for joining me. All right. So yesterday I couldn't stream, but today, let's switch over here. Here we go. I've completely forgotten where we left off. So we were working on the code in this section to see if we could make sure that we don't use this outside of a class. That's what we were working on, and we sort of kind of got partway through and then failed before we ran out of time. So I think we were in the compiler, right? And we were inside class declaration. Right, yes, replace current class with the new one and pointing closing class back to the previous one, and then down here, replace the new class with the previous one. I remember that. So, and then what did we have? We changed the compile result to have the current class in it. And then outside here in this, we would have to check the compile result and see if we're compiling a class or not. Right, that would go in here somewhere. Okay, so how do we do this part? That's where we were hung up, right? Trying to figure this part out. So current class is not used anywhere. Let's class declaration. There we go. It wasn't gonna be too bad, right? So let prev is equal to self result borrow current class replace with what does it need to be replaced with? A sum rc new class compiler new. Right? That's what we tried, and then something was failing. Does that line work? Yes. And then we need access to this class compiler to put its enclosing value here. So then self results borrow current class, and then we have to borrow that, borrow mute, unwrap, no, borrow, unwrap. Right, so we borrow to get to the ref cell, we unwrap to get through the option, and then we're going to, we have the class compiler, we should be able to say enclosing, then we're up here, borrow mute, oh, actually replace with prev, right? We want to replace, because this enclosing should be none, and we should be able to replace it with prev at this point. Does this line work? I think this was the line we were stuck on, yeah. Oh, current class doesn't have that, and that doesn't like that. We have to do an asref. I've noticed that the compiler error message always puts the asref after the unwrap, but we always want it before the unwrap. And I'm not sure what's up with that. If I do it after, right, it fails. Right? It's saying, help consider borrowing the options content. So I think this error message must be buggy. Right? If I switch it around, then it works. Okay. And then after we're done, we want to pull this one out. Yeah, I have this line here. I think what we want is let prev equals, we got to get the previous one back out. Self result borrow current class borrow asref unwrap enclosing replace with none, and we get the old one out, and then we can say self result borrow current class replace with some prev, or maybe just prev. Right, so we pull the old one out here into previous, right, and then put it where it belongs, and that fails. Oh, because I keep doing that. And this is where it goes. There we go. Okay, so now we have no errors. So that's these two lines here. When an outermost class body ends, enclosing will be null, so this resets current class to null. In our case, it's a none. So whatever the old one was is going to be none. So if we're inside a class and therefore inside a method, we simply check the module variable. So we just look at current class to see if it's none. So that's in the this function. We can say if self dot result dot current class dot borrow is none, then we'll say self error. Is that a function? Error? Error at? Oh, just error. Yeah, okay. Self error can't use this outside of a class. Return. Otherwise, it's a variable. Okay. Does that work? Nope. Oh, borrow. Okay. So does this actually do the thing that it's supposed to do? So the errors that we need to catch are these two errors, right? Print this and print this inside a method. And the idea is we're catching it at the compiler level rather than at the runtime level. We were able to catch it runtime, by saying it's undefined. So cargo run. Print this. So now we catch it at a compile time. Error at this, can't use this outside of a class. So we're seeing that error. And the other error is fun not method print this. And again, we concede that. But the other class stuff should work. Locks. Like person here. We should be able to print Jane, right? Cargo run person. Ooh, okay, so this isn't working. Why not? That's interesting. Why is this not working? Current class is going to be... Well, it's obviously none at this point here, but we're creating a new one here. So when we do, so we're inside where? Let's take a look at this is nested, right? So this is the equivalent here. Because person is calling, I should look it up, person. That way we can look at it, right? So there's a method. We started a new class, which is this class declaration here, right? We declare the variable person, and we keep running, and then we call method. So what does method do? Method calls function, and function, and function, function's replacing the compile result. So that's not good, right? Because now we're getting a brand new compile result, and this now is, or current class is now none. So this doesn't belong here. We can't put it in compile result. We have to put it in the overall compiler. Which is called what? Is it just called compiler? I don't even remember where it goes. This is the parser. Here's, no, this is impl compiler. It's struct compiler. Okay, so what if we put it here? Because we're not creating a new compiler each time, but we are creating a new result for every function. So we need to keep track of it in the current class instead. I mean, in the current compile scope, I guess. So, where was I? That means down here, it's not self result borrow current class, it's just self current class borrows none. And that removes those two lines, and that removes those two lines. That removes those two. And that removes those two, right? I think that's all we need to do to move it up one level. It's still kind of long. Current class borrow as ref, unwrap, and closing replace. But, oh, and it doesn't compile because, oh, we need to move it here. So current class, oh, because we don't have a default for compiler, whereas we had a default for the other one. So all we have to do here is current class ref cell new none, right? Okay, now we have no errors and no warnings, and we should be able to run person. Yep, and it prints out Jane correctly. Cargo run. Oh, let's just do this, print this, make sure that works. And I always restart this after an error because it seems to mess up. What was it? Fun, not method. Print this. Okay, can't use this outside of a class. Okay, perfect. can we run all of these locks things now? Cargo, build, release, no default features. And then we'll run that for loop, which I've lost now. There it is. Okay. Yep, target release lock spike code on $I done. Okay, so let's see what happens. Yep. Oh, no, it panicked. That's not good. Oh, it is broken. But we're not supposed to be getting a panic there. Cat broken. I mean, the compiler shouldn't panic. Index out of bounds. So len is 11, but index is 15. All right, so we have a bug that we need to fix. Not right now though. Let's get this committed. Right, we just finished the whole this section. So this is 28.3 this, and then we'll take a look at this broken bit of code here. Git status, git add source, git commit -m section 28.3 this. Clippy is happy, and we don't have any tests. Okay, so let's take a look at what's going on here. Let's cargo run it in debug mode. Oh, I see. It looks like it's popping up the stack for the errors, and it's failing. Epic says, I don't know why, but I'm always fascinated by seeing disassembled dumped code. Yeah, we can see what our compiler is generating. I wonder what it would take to get this to emit like x86 instead of VM code. That would be interesting, because these are very high level, right? Closure. I mean, that's not really an opcode that you would see on a bare metal chip, right? But it looks like what we're trying to do is pop up the stack here. Line 4 in C. It should be 1, 2, 3, 4. Yeah, so here in C, and then line 2 in B, and then line 1 in A, and then line whatever this is, 7. That's what it should be, and it looks like we're popping up the stack incorrectly, and that's why we're failing here. Epic says, starting to think in terms of JIT. Yeah, okay. I wouldn't know how to translate closure into, I mean, it obviously would just be like a procedure that you JSR to, right? But there would be a lot involved in that. And memory management, right? I'm not doing any of that in this code. It's all handled by the interpreter. So there's a lot of infrastructure that would have to be written first in order to get this to work. Let us take a look. I think it's in VM where we print out the stack trace. Yeah, so for frame in cell frames, it'll reverse. And then we take a look here. Let's print out the frames. Can we do that as a debuggable thing? Like this. Well, it didn't complain, so let's take a look at what it dumps out. Yeah, maybe I should iterate over them and print each one with a separator so I can see where all the call frames are. Because here's a call frame. Here's a call frame. They all say line 11111. Here's line 44444, 55. So we have the correct line numbers in there. It's just that we're not. I mean, it's saying line 4 in C, right? So here's line 4, and then we should be going back to line 2. Whoops. For this call frame here, right? So there's a call frame there with line 2, but we're seeing line 4 in C. So there must be. Let me print out each frame as we hit it. Println frame, like that, and we can print out the debug of it. Oops, too many of those, and then just say frame here. Right. So run that and take a look at each frame. Yeah. So it's doing this, line 4, and it's doing this, and it's still saying line 4. So there must be... Okay, let's take a look at the code. This would be easier to see it side by side. But it is what it is. Okay, so here's the instruction, is in the frame IP borrow -1. And then line is self chunk. Oh, self chunk get line. We need the frame. That's what changed. That's what changed. Okay, FN chunk. We're always getting the current frames chunk instead of the actual frames chunk. So what we need to do is say frame. How do we get the, where is this? Oops. Frame last unwrap. It gives us a call frame. So I should be able to say frame get chunk like that. Get rid of this. Call frame doesn't have a get chunk. Oh, it has a closure. And closure, I bet, has get chunk. Is that right? Yes. Okay, so that's what I was missing. So frame dot closure, oops, dot get chunk. And then this will also have to be frame closure stack name. Can I do that? Like that. Let's run that. Yeah, okay, so now expected 0 arguments got 2, line 4 in C, line 2 in B, line 1 in A, and line 7 in script. Okay, so now that's working. Good. Yeah, I had refactored the whole call frame thing. Oops. And let's get rid of this print line here so we don't see all that. Yeah, that's better. And then, but of course, I don't have tests, so I didn't realize what I broke. Internet Bird says, hi, are you studying Rust? Yes, I am trying to learn Rust, and the way I'm learning Rust is by porting something from C to Rust. Okay, so we got this working. We got this bug fixed. Git status, git add source, git commit, fix error, or stack dump code. There we go. Okay, so now we're up to instance initializers. The reason object-oriented languages tie state and behavior together, one of the core tenets of the paradigm, is to ensure that objects are always in a valid, meaningful state. When the only way to touch an object's state is through its methods, the methods can make sure nothing goes awry. But that presumes the object is already in a proper state. What about when it's first created? Object-oriented languages ensure that brand new objects are properly set up through constructors, which both produce a new instance and initialize its state. In locks, the runtime allocates new raw instances, and a class may declare an initializer to set up any fields. Initializers work mostly like normal methods with a few tweaks. Of course, locks does let outside code directly access and modify instances fields without going through its methods. This is unlike Ruby and Smalltalk, which completely encapsulate state inside objects. Our toy scripting language, alas, isn't so principled. Yeah, it's relying on the programmer to be principled about it. The runtime automatically invokes the initializer method whenever an instance of a class is created. The caller that constructs an instance always gets the instance back after the initializer finishes, regardless of what the initializer function itself returns. The initializer method doesn't need to explicitly return this. In fact, the initializer is prohibited from returning any value at all, since the value would never be seen anyway. Now that we support methods, to add initializers, we merely need to implement those 3 special rules. We'll go in order. It's as if the initializer is implicitly wrapped in a bundle of code like this. Note how the value returned by init is discarded. Okay. So we create a new instance. This is a implicit thing, so this doesn't exist, right? And then we do init and then return obj. Okay, so invoking initializers. First, automatically calling init on new instances. So in call value, new instance. Oh, this is here in this section. Let's put some spaces here to separate the thing. But when we create the class, now we're going to look up to see if the class has a method called initializer and then call it. Okay. How hard is that going to be? Table get class methods. So we should have a way to get the method on classes. Let's take a look at our class code. Add method, get method. Right, so we just call get method on it. So let initializer, we can say if. Let some initializer, because it might not exist, is equal to class. We have the class here. Class.get method VM init string. What is that? I thought we were just looking up init, right? Like that. And then return call as closure. Well, let's just put this in as a placeholder for now, and we can figure out what init string is later. So all we need to do is say self call initializer arg count else true, right? And that returns that. Does that build? It does not. A move occurs. We're moving it into here. Okay, so we should grab the initializer first. Let initializer is equal to class get method init, and then we can pass it in here and it'll move. That'll be fine. And then we can just say let's call this one init. We'll call it init here. How's that? Okay, that's better. Yay, borrow checking. Okay. So let's keep reading and figure out what this init string is. After the runtime allocates a new instance, we look for an init method on the class. If we find one, we initiate a call to it. This pushes a new call frame for the initializer's closure. Say we run this program. When the VM executes the call to Brunch, it goes like this. So we have Brunch class, we have eggs, we have coffee. It's pointing to a new instance with eggs and coffee. All right. Any arguments passed to the class when we called it are still sitting on the stack above the instance. The new call frame for the init method shares that stack window, so those arguments implicitly get forwarded to the initializer. Well, let's see if this... we're only partway through this, so I don't know if it's going to work. But we can... Bagel blocks. Oh, Brunch. So let's copy this over. Oh, I already have a Brunch. Well, that's all right. We can blow that away. It wasn't doing much anyway. Right? If I say cargo run Brunch now, I don't know what's going to happen. It ran. We can see eggs and coffee. We see the Brunch instance with eggs and coffee, and then this nil. So I'm not sure exactly what happened, but we're not really quite there yet. We are defining global. We are calling the global Brunch with arguments eggs and coffee. So it's doing something. So I think whatever we did is working. It's just not quite there yet. Locks doesn't require a class to define an initializer. If omitted, the runtime simply returns the new uninitialized instance. However, if there is no init method, then it doesn't make sense to pass arguments to the class when creating an instance. We make that an error. Okay, so that's true. If I say cargo run, and I say class foo that doesn't have, it does not have an initializer, then if I say var f equals foo with an argument, it should fail. And it doesn't fail right now. It should give us an error saying there's no expected 0 arguments but got %t. Okay. Nope. Okay, so else if arg count is not equal to 0, then we're going to say self runtime error, expected 0 arguments, but got arg count. And then we're going to return false. Else. 2 warnings. Oh, it has a result that must be used. Okay. Really? Are there other? Yeah, see, I just throw it away there. I throw it away there. Here, I actually return runtime error. Okay, so I guess it's useful to have. You just have to say let underscore like that, so the warning goes away. Just same thing as like casting it to void in C. Okay. So now we should see that error if we try to use it, right? Class foo var f equals foo. Let's just do that. There we go. Expected 0 arguments, but got arg count. Oh, that failed. You can fix that though. Format. There we go. All right, so that should fix that error, or that mistake. When the class does provide an initializer, we also need to ensure that the number of arguments passed matches the initializer's arity. Fortunately, the call helper does that for us already. Okay, so we can verify that too. Cargo run. If I say class foo init abc print hi, I don't know, do something. So there's our class foo, and then we can say var f equals foo and don't give it any arguments. Expected 3 arguments but got 0. But then it also says can only call classes and functions and classes. So we're getting double errors. That's a result. So that's probably going to blow us up when we run our test suite, when the full-on test suite runs. That's right. We'll fix that then. I'm not going to worry about it now. All right. To call the initializer, the runtime looks up the init method by name. We want that to be fast since it happens every time an instance is constructed. That means it would be good to take advantage of the string interning we've already implemented, which I didn't do. I see. To do that, VM creates an ob string for the init and reuses it. The string lives right in the VM struct. Okay, so the fact that we have to use in the C code, we have to use an ob string to look up the init function is why we have to go through that, and then we just create one at the beginning of the program. We create an intern string when the VM boots up, so it's just stored in the, but yeah, it's just stored in the VM, but in our case we don't have to worry about that, so because we can just throw it in here and it gets compiled right in. But it gets initialized here, copy string init4. We want it to stick around so the GC considers it a root. So we mark it in mark roots. Look carefully. See any bug waiting to happen? No, it's a subtle one. The garbage collector now is VM init string. That field is initialized from the result of calling copy string. But copying a string allocates memory, which can trigger a GC. If the collector ran at just the wrong time, it would read VM init string before it had been initialized. So first we zero the field out. Oh, I see. It would look in init string because it gets marked during the mark roots. But if this is null or it's garbage, stack garbage or whatever, I see. I get it. And clear the pointer when the VM shuts down since the next line will free it. Okay, that lets us call initializers. Initializer return values. The next step is ensuring that constructing an instance of a class with an initializer always returns the new instance and not nil or whatever the body of the initializer returns. What are we doing here? I guess, is it returning nil? I mean, that's what it looks like, right? We're getting a nil return value. But does that matter? If I say var class foo with an init that just says, print hi, right? Is that, oops. Oh, I did it wrong. Okay, let's try again. Class foo, like this, init, print hi, like that. Okay, so now we've defined a class foo. If I say var f equals foo, we now have f. If I say print f, it should be an instance of foo, and it's nil. Yeah, so this nil is coming back. So maybe we just need to pop the nil or not push it on there or something. Let's find out. Right now, if a class defines an initializer, then when an instance is constructed, the VM pushes a call to that initializer onto the call frame stack. Then it just keeps on trucking. The user's invocation on the class to create the instance will complete whenever that initializer method returns, and it will leave on the stack whatever value the initializer puts there. That means that unless the user takes care to put return this at the end of the initializer, no instance will come out. Not very helpful. To fix this, whenever the front end compiles an initializer method, it will emit different bytecode at the end of the body to return this from the method instead of the usual implicit nil most functions return. In order to do that, the compiler needs to actually know when it's compiling an initializer. We detect that by checking to see if the name of the method we're compiling is init. Okay, so we have function, initializer, and method. I think I kind of ignored some of that, didn't I? We have script, function, and method. So it looks like we're going to add an initializer to this. And up here in method itself, we're going to check to see if we have a parse token lexeme. I see. So here in self chunk type method, we can just say if parse token lexeme equals init. Will that work? Then it's going to be chunk type initializer else chunk type method. Nope. Oh, it's not a method. Okay. So now we call function with the correct type. Whenever the compiler emits the implicit return at the end of the body, we check the type to decide whether to insert the initializer's specific behavior. So if the type is an initializer, we're going to emit get local 0. Otherwise, we're going to emit the nil and then emit a return. Okay. Emit return. So there's the nil that we already emit. So we can just say if self dot, get to see where is that getting stored. C type. It's in result C type. Okay. Self result borrow C type is equal to chunk type initializer. Then we're going to self emit bytes, opcode, get local, 0, else, that, right? That looks correct? Okay. All right, that works. In an initializer, instead of pushing nil onto the stack before returning, we load slot 0, which contains the instance. This emit return function is also called when compiling a return statement without a value. So this also correctly handles cases where the user does an early return inside the initializer. All right. So if I say cargo run now, say class foo, init, print hi, close, var f equals foo. Now we see foo instance on there. It called the initializer and printed hi. And if I say print f, it should be a foo instance. And it is. Okay, so I fixed that problem. Good. And then we have incorrect returns in initializers. The last step, the last item in our list of special features of initializers is making it an error to try to return anything else from an initializer. Now that the compiler tracks the method type, this is straightforward. All we have to do is look in return statement. If is matched token semicolon, emit return, else if self dot result dot borrow dot c type is equal to chunk type initializer, then we're going to call error, but we're going to keep going. We'll still go ahead and compile the value afterwards. The compiler doesn't get confused by the trailing expression and report a bunch of cascaded errors. Okay. So we'll just say self error can't return a value from an initializer. Okay, that should work. Yep. We report an error if a return statement in an initializer has a value, right? Aside from inheritance, which we'll get to soon, we now have a fairly full-featured class system working in Timelocks. All right, so let's just check this error return business. Cargo run class foo init return 12, and that should fail to compile. Error at return can't return a value from an initializer, but if I say class foo and just make a regular function, return 12, it should work. And it does. Okay, good. All right, so we should be able to make this coffee maker thing work, right? Let's see if this all works. Look at that. Enjoy your cup of coffee and chicory. No reusing the grounds. All right, well, I mean, it all seems to have worked. What did it compile into? Here's coffee maker, here's the init. It's called to init when we call coffee maker. We push the constant coffee and chicory on the thing, and we call brew. And brew just puts enjoy your cup of, and it grabs the coffee property and prints it. Okay. Neat. So that all worked. Pretty fancy for a C program that would fit on an old floppy disk. I acknowledge that floppy disk may no longer be a useful size reference for current generations of programmers. Maybe I should have said a few tweets or something. How old were old floppy disks? Floppy disk capacity. 1.44 for the 3.5. What about the 5.25? Originally designed as a single-sided low-density format with a storage capacity of 100 kilobytes. All right. 5.25-inch diskettes were available in a capacity of 160. I guess it depends on what computer was running it, but I guess different computers had different storage packing methods. All right, so 160K. What do we have in terms of? We have 82K. Well, less than 82K. Around 80K. So this could fit twice on a single-sided floppy disk, low-density floppy disk. Okay, cool. Git add source, git commit -m, and what section is this? This is methods and initializers, right? Instance initializers, right? Section 28.4, instance initializers. Clippy's happy with it. Cool. All right. So now we're up to optimized invocations. Our VM correctly implements language's semantics for method calls and initializers. We could stop here, but the main reason we're building an entire second implementation of locks from scratch is to execute faster than our old Java interpreter. Right now, method calls, even in C locks, are slow. Are they? Can we write a quick program to see how slow they are? And then we can compare the code. Let's do method call time locks. So we can just create a function called foo, which doesn't do anything. Then we can say var start equals clock. We can say for var I equals 0, I is less than, how far should we go? 50 million? I plus plus foo. I don't know why I put a space there. That, and then we can just say var end equals clock, and then we could say print the total time was, print end minus start, print milliseconds. I can't, we don't have good formatting code yet. Can I add strings to values? Var total time end minus start. Can I do this? Total time plus ms. I don't know if that'll work. Okay, so let's go into locks AST, cargo build. I think I already built this, right? Release. And see how long it takes for the AST version to do this. Locks AST, target, release, locks AST, method call time. Yeah, so we can't do that. So let's just change this back. Just keep it simple. We can always add that as a feature. Oh, like that. And we need a semicolon there. Oh, I missed the semicolon. Oh, maybe that would have worked. Okay, let's undo all that. Put the semicolon there. Let's try again. Nope. All right, epic fail. Yeah. Print. And put a colon back there, just because. Okay, so this should work. No. Line 4. Oh, I can't do I++. I equals I plus 1. So that was the problem all along. So I probably could have done that thing. Okay, so 50 million may be too long. Let's do 5 million. Still very long. There we go. Okay, so it took 6.6 seconds, right? And if I run, let's build the locks bytecode. Cargo build release no default features. Right? And then we can run that. Locks bytecode target release locks bytecode method call time. Operands must be 2 numbers or 2 strings. On line 4. So we have a bug in our code. Right? Line 4. Oh, what's it doing wrong here? We don't have for loops working? Did I break for loops along the way? Because it looks like it's comparing the number with a native function instead of the I. Oh man, did I break this? Okay, well I'm glad I went through this check then. Locks bytecode. So we need to fix this. Git status. What are we at? We don't have anything changed. So let's fix the for loop. Do I have any for loops in our grep? For star locks. Yeah, I have for loops in here. Cargo run for func test. Locks bytecode. No. Target release locks bytecode for func test. That works. But this doesn't. Wow. Okay. I guess we should run it like this and see where it breaks. So here we got clock. Native function never got popped. Oh. Oh, so we have a bug in our native function handling code. We're not popping off the native function after calling it. Is that in our VM that's failing? Call value. Here we're still self-stack truncating. Maybe this is truncating too short. I don't want to do this. So that'll generate 1,000,000. But we can at least, we can test it, right? If I say native test locks var c equals clock, var m equals 12, print c, print m. So this should fail, right? I don't want a cargo run. Target, release, no, debug. This is before I changed the code. No, that still works. That works, but it's still, it left native function on there, right? That shouldn't be on the stack anymore. So if I say cargo run native test, no, it's still there. It's still on the stack and it shouldn't be. And it looks like it didn't make a difference changing the, it looks exactly the same, doesn't it? Yeah, after here, this should pop the native function off. And I changed this line here, so this should have changed println truncating stack to this stack top minus arg count plus 1. That's what I had originally. right? So let's see what this says when we run this. Truncating stack to 3. But there's only 2 things on the stack. Here's the call. The resulting stack should have this value on it, and then this result is this. Okay, let's take a look at that. Result is this number. So we need to pop both of these things off the stack. Right, because if I just have a native method that returns a number, a non-native method that returns a number, fun foo, return 12, var f equals foo. We should see that, oh, and then print. So there's some code after it. Non-native. So return, the fun foo comes off the stack, and then 12 gets pushed onto the stack. And so that way f gets defined to be 12. Here, we're calling this, so it should push this onto the stack and then define global C, but C looks like it, C gets defined correctly because it put that on the stack and then printed it. But for some reason, all right, we're going to have to go back. We're going to have to go back over here because that way I'll see a, what is this? Oh yeah, that's the next thing I want to do. Okay, so crafting interpreters. We got to look at, I guess calls and functions would have the native stuff in it. Let's see what we did wrong here. Native functions, yeah. All right. So this is the native function. That's creating the objects. Here's call value. Result is native VM stack minus equals arg count plus 1. Stack top. Oh, we're subtracting arg count plus 1. Okay. Is that what we're doing over here? Let's take a look. Carino, thank you for the raid. How was your stream? Were you working on Rust stuff too? I thought I'd look to see Rust streams, but I didn't see your name on the list. All right, so I think what's happening here is we need to subtract arg count plus 1 from stack top, right? I think that's what the equivalent is supposed to be. Yeah, now it pops off the native function, and that all works. Okay, so cargo build, release, no default features. Okay, so I think that fixed that bug. And now we should be able to say method call name locks bytecode. Oh, now it's bad. Cannot run file OS. Oh, right. We need a better error message for can't find file. Oh, I gotta also delete that line. All right, so this is slower, right? Let's rerun the locks AST. Right, and this is the Rust version of the Java code. Okay, it's about the same speed. We got 6.6 seconds the last time we ran this. So maybe we should run it 10 times and let's see, 110. Do this, done, and we can see what the averages are. Well, you know, I'll obviously take a minute to run all of this, and we don't need all of this business. We can just print out the number. So this is getting about 6.7. Got a 6.9 there. I'm not sure why. It is single-threaded, but LOX code is single-threaded anyway. So both the interpreter and the LOX code. So it's 6.9 to 6.7, and then if we run the bytecode version of it, we're going to see this thing. I gotta clean that up. 7.1. So it's definitely slower by a reasonable margin. Oh no, it's about the same. Although the low end here is probably different to the low end here, right? That might be the low end, and the high end here is yeah. So this is like 6.7 to 6.9, and this might be 6.9 to 7.2, right? Okay, so it's slower, but not that much slower. So let's get rid of this, and now we have this fixed. Git add source, git commit, oh, you can show staged, git diff staged. Yeah, so that was the only change. Git commit -m fix bug with native stack popping. Good. All right, so let's go back here to where we were, and we were looking at, that's not what we were looking at. What's going on? Classes and instances, garbage collection. I wonder what the hell just happened. Jumping back and forth. This is weird. What happened to my... I was down here in methods and initializers. Here we go. And we were near the bottom. So let's go up a couple pages. Optimized invocations, right? This is where we were. And we were trying to time the difference between LOX bytecode versus LOX AST. And they're about the same size speed, although LOX bytecode is slower. LOX's semantics define a method invocation as two operations, accessing the method and then calling the result. Our VM must support those as separate operations because the user can separate them. You can access a method without calling it and then invoke the bound method later. Nothing we've implemented so far is unnecessary. But always executing those as separate operations has significant cost. Every single time a LOX program accesses and invokes a method, the runtime heap allocates a new object-bound method, initializes its fields, and pulls them right back out. Later, the GC has to spend time freeing all those ephemeral bound methods. Most of the time, a LOX program accesses a method and then immediately calls it. The bound method is created by one bytecode instruction and then consumed by the very next one. In fact, it's so immediate that the compiler can even textually see that it's happening. A dotted property access followed by an open parentheses is most likely a method call. Since we can recognize this pair of operations at compile time, we have the opportunity to emit a new, special instruction that performs an optimized method call. If you spend enough time watching your code VM run, you'll notice it often executes the same series of bytecode instructions one after the other. Classic optimization technique is to define a new single instruction called a super instruction that fuses those into a single instruction with the same behavior as the entire sequence. One of the largest performance drains in a bytecode interpreter is the overhead of decoding and dispatching each instruction. Fusing several instructions into one eliminates some of that. The challenge is determining which instruction sequences are common enough to benefit from this optimization. Every new super instruction claims an opcode for its own use, and there are only so many of those to go around. Add too many, and you'll need a larger encoding for opcodes, which then increases the code size and makes decoding all instructions slower. Alright. Classic speed versus space time trade-off. So we'll start in the function that compiles dotted property expressions. So in our compiler, we have a function called dot. We're going to add this new else if self is match token type left paren. Then we're going to do this. Argument list. Does that already exist? I've forgotten already. Self emit bytes, opcode invoke, name, emit byte, arg count. Yes, so argument list already exists. So we're short-circuiting the whole get property thing. After the compiler as far as the property name, we look for a left parenthesis. If we match one, we switch to a new code path. There we compile the argument list exactly like we do when compiling a call expression. Then we emit a single new op invoke instruction. It takes two operands. The index of the property name in the constant table, the number of arguments passed to the method. In other words, this single instruction combines the operands of the opget property and opcall instructions it replaces in that order. It really is a fusion of these two instructions. Let's define it. All right, so in chunk, we add a brand new invoke. Of course, we have to add that down here too. Okay. This is a new special instruction format, so it needs a little custom disassembly logic. All right, let's go to the disassembler. Opcode invoke. Oh, it's just self invoke instruction. So, you know, these were all pulled out, right, as separate things. I don't know why closure got to be an inline thing. Op invoke. Maybe we should clean that up at some point. All right, so down here at the bottom, CFG, let's just copy paste. Oops. There. Function, invoke instruction, self, name, stir, offset, usize, and returns a usize. Okay, let constant is equal to self.code offset +1. Let arg count is equal to self.code of offset +2. Print. Okay, this does not have a new line on it. We're going to do name :-16, which matches all these guys. We'll do a arg count, args. I guess we don't care that this is not going to line up. And then we just do a constant :4. That's interesting because it's going to just push everything out. All right. And then open single quote, self constants dot print value constant as usize, and then print ln this closing quote, and then return offset +3. Oops, there. We read two operands and then print out both the method name and the argument count. Over the interpreter's bytecode dispatch loop is where the real action begins. All right, so this should all check, and it should pop us over to the VM. Oops. VALUE. There. Okay, so now opcode invoke. So what are we going to do? Read string. We're going to read a byte. If we can't invoke the method with the argument count, we get a runtime error. Otherwise, we pop the frames. Okay. So we should be able to look at call and see something similar. And get property, right? It's a combination of get property and call. Where's get property? Here's get property. Yeah, so this is our read string, right? This is how we do read strings. And this is not field name, but it's method name. Okay, and then the way we get the arg count is the same way as in call. All right, and then we try to invoke. Oh, here's invoke. Okay. So then we just say if self invoke method name our account, then we'll return the error, return error. Oh, and we just return a runtime error. Okay, interpret result runtime error. Otherwise we pop the frame. In call, we're not popping a frame. That's interesting. Where do we pop the frames then? Right, here's call. Or maybe in return? If self frames is empty, self pop return OK. Self stack truncate previous frame slots. This is just setting frame to frame count -1. Maybe we don't need to do this because we're just, this is going to push. Okay. Let's see what happens if we ignore this, because this is just setting the frame to the last, and we already have code that grabs the last frame, so we don't need to do anything else. There. So this should work, except for the fact that we don't have an invoke function. Most of the work happens in invoke, which we'll get to. Here we'll look up the method name from the first operand and then read the argument count operand. Then we hand off to invoke to do heavy lifting. That function returns true if the invocation succeeds. As usual, a false return means a runtime error occurred. We check for that here and abort the interpreter if disaster has struck. Finally, assuming the invocation succeeded, then there is a new call frame on the stack. So we refresh our cached copy of the current frame in frame. Yeah, okay, so we don't need to do that because that's handled for us here. When we try to get the current chunk, we always look up current frame. The interesting work happens here. So this batch loop is where the rail action begins, and the interesting work happens in the invoke function. Got it. Let's function call value. So after this, we'll say function invoke. Name is going to be, what are we passing in? String, maybe? And then our count is going to be usize, and it returns a bool. Okay, and then this says let receiver is equal to self peak of our count. How is that done up here? Yeah, arg count borrow clone. Okay, and then because this is just going to be an RC. Oh no, it's a value. We're cloning the whole value. And I guess we have to clone it out because we're borrowing it, right? And then let instance is equal to, if let value instance is equal to receiver. And that should be an RC of instance, right? Yep. Oh, I like how it just sits there. That's terrible. Okay, and then we're going to return invoke from class, self invoke from class, instance, get class, name arg count, which this doesn't exist, else false. Right? If the thing is not an instance at this level, then we're going to just return false and let the runtime error occur. Invoke from class doesn't exist. Okay. First, we grab the receiver off the stack. The arguments passed to the method are above it on the stack, so we peek that many slots down. Then it's a simple matter to cast the object to an instance and invoke the method on it. That does assume the object is an instance. As with the opt-get property instructions, we also need to handle the case where the user incorrectly tries to call a method on a value of the wrong type. All right, so I got to put this error in there. April Gupta, thank you for the follow. All right, so let's report the error here. Self runtime error. Oops, should be lowercase. Only instances have methods. There. So that should, except for this invoke from class. That's a runtime error, so we report that and bail out. Otherwise, we get the instances class and jump over to this other new utility function. As you can guess by now, we split this code into a separate function because we're going to reuse it later, in this case for supercalls. Okay, so we're going to say fun invoke from class. What self? I'm going to say class is going to be RC class, I hope. What does get class return? Oops, why is this not working? There. On instance. So we have get class, which returns an RC class. Okay, so yes, this will be an RC class. Then we have a string, name string, and then arg count, use size, and it returns a bool. Okay, so if I do that and just say false here for now, just to see what happens. Okay, so that all compiles, which means we have everything correct. Value method, table get, class methods, name methods, runtime error, undefined property, name chars. So we should be able to say if let value closure, right? It should be a closure. That's what I'm reading here. It shouldn't be undefined property, right? It should be undefined method. Okay, well, I'll leave it. Closure is equal to class dot get method name, right? Then we're going to say return self call closure arg count. Else self runtime error undefined property name. I want to be correct with my error messages here because the test suite checks the error messages exactly false. There. Does that build? It does not. Of course not. Closure. Name doesn't work. Expected stir found. Okay, so this needs to be as stir. Oh, we can just pass it in that way, right? This expression is type option. Okay, so this should be some. Option closure. My mistake. There's no value in there. And now expected stir found string. Can I do that? Or do I have to do it as string? No. And the warnings are... Oh, right, those guys. And I misspelled instances. Let underscore equal. Let underscore equal. Okay, so that cleans up all that. This function combines the logic of how the VM implements get property and opcall instructions in that order. First, we look up the method by name in the class's method table. If we don't find one, we report that runtime error and exit. Otherwise, we take the method's closure and push a call to it onto the call frame stack. We don't need push a call to it. I guess that's what this means, right? We don't need to heap allocate and initialize an object-bound method. In fact, we don't even need to juggle anything on the stack. The receiver and method arguments are already right where they need to be. This is a key reason why we use a stack slot 0 to store the receiver. It's how the caller already organizes the stack for the method call. An efficient calling convention is an important part of bytecode VM's performance story. If you fire up the VM and run a little program that calls methods now, you should see the exact same behavior as before. But if we did our job right, the performance should be much improved. I wrote a little micro benchmark that does a batch of 10,000 method calls, then tests how many of these batches it can execute in 10 seconds. On my computer with the new op invoke instruction, it got through 1,089 batches. With the new optimization, it finished 8,324 batches in the same time. That's 7.6 times faster, which is a huge improvement when it comes to programming language optimization. All right, so now we're going to see if this even works, right? So let's build release with no default features. And then for I. There we go. Let's see what happens. Will it be faster? And will it be 7.6 times faster? It's not looking 7.6 times faster. In fact, it's slower. Excellent. Excellent. Well, I mean, I shouldn't be running benchmarks on a program that, on a computer that's also running OBS and Pretzel Rocks, right? Maybe I can do this offline. But this was supposed to be faster, right? Let's see if we're actually even using... Yeah, this is definitely slower. Locks bytecode. If I say cargo run non-native.locks, I don't see invoke. I don't see invoke. Oh, maybe this is... Oh, this is just class-based stuff. Oh, okay. And I'm not calling it class-based thing. I'm just calling this. I should be calling a class-based thing. Class, foo. And then we'll create a function called foo in there. And then we'll have to say var f equals foo. And then call f.foo. Right? And I'll forget this and I'll forget that. We'll just print out the total time. Okay, so now let's run the bytecode version. I mean the AST version of this. Ooh, what did I do wrong? I put a 0 there instead. Okay. Expect method name. Oh, right, you don't put fun for class methods. All right, so let's see how slow class methods are. Is it going to be around the same time, around 6 seconds? No, it's 14 seconds. Wow, okay, so calling class methods with the AST thing is very slow. Now I wish I had saved the old locks AST. You know what we can do is just comment that part of it out, right? I mean the locks bytecode version. Let's comment out, yeah, so this is around 14 seconds per invocation. Right, so if I go locks bytecode, source compiler, and look for the invoke instruction. Let's comment this part out, right? So we don't do it. Let's release. Oh, I keep doing that. Release, there. And it's going to warn us about unused invoke, right? Oh no, it didn't. Okay. And now let's run that in the bytecode version. And let's see, is this any faster than the AST version without the extra invoke capability? It is faster. Okay. So that's 10.5 seconds right there. Let's let it run a few times. Yeah. So between 10 and 11 seconds, whereas this was between 13 and 15 seconds, right? Around 14 seconds. This is around 11 seconds. Okay. So that's good. And now we'll put that back in. All right. Let's put that back in. Oh, why did that not? There we go. Okay. I was wondering why it wasn't reformatting. Okay, so now that's built. Let's build it. And let's try it and see if it goes any faster than 10 to 11 seconds. There it is. It's faster, but it's not 7.6 times faster. Right. It's about 8 seconds or so versus 11 seconds, right? So I mean, it's not insignificant. It is a significant improvement, but it's definitely not 7.6 times faster. So, all right. Where are we doing? Oh, invoking fields. The fundamental creed of optimization is thou shalt not break correctness. Users like it when a language implementation gives them an answer faster, but only if it's the right answer. Alas, our implementation of faster method invocations failed to uphold that principle. So if we have an oops thing. Well, let's run this. We can just run this thing so we don't see all the bytecode. Oops. Undefined property name. Ooh, okay, there's a good bug I need to fix. Undefined property name. There it is. Format. Do we have any others? That's in a format, that's in a format. Okay, so I think they're all good. They all have formats. Good. Cargo run. Oops. Let's see what. Ooh. I forgot the bang. There we go. Cargo run. Oops. There it is. Undefined property field. Line 12 in script. Okay. So we broke something. And where's our new invoke? Here it is. See how it's put this over here. That's kind of nutty. I would have done it the other way around. Put so that this thing would line up here, and then we could put 0 args afterwards. Anyway, it is what it is. The last line looks like a method call. The compiler thinks that it is and dutifully emits an opt-invoke instruction for it. However, it's not. Cases where users may be satisfied when a program sometimes returns a wrong answer in return for running significantly faster or with a better bound on the performance. These are the field of Monte Carlo algorithms. For some use cases, this is a good trade-off. Important part, though, is that the user is choosing to apply one of these algorithms. We language implementers can't unilaterally decide to sacrifice their program's correctness. Okay. What's actually happening is a field access that returns a function which that then gets called. Right now, instead of executing that correctly, our VM reports a runtime error when it can't find a method named field. Yeah. Earlier, when we implemented opt-get property, we handled both field and method accesses. To squash this new bug, we need to do the same thing for op-invoke. Okay, so in invoke, here's where we grab the instance, and now we're going to check the value. We're going to say if it's a value, then we're going to do this, else we're going to do this invoke from class. Okay. So if let some instance, no, is some value, right, equals instance get field name. Then it's going to set the stack top to value and a return call value. Okay, how do we do that in get property? Oh, I see. We popped and pushed. And here we're just setting, instead of doing a pop push, we're just going to replace arg count -1. Okay. So we're going to have to do that. And then grab this and set it equal to value. That's similar to this, right? What is value? Will this tell me, even though this stuff doesn't compile? It is a value. So I can say RC new ref cell new value. Is that what gets pushed onto the stack? I've forgotten already. And then we just say self in call value. Ooh. Value arg count. That's not going to work because we need to clone the value onto the stack, right? Else this thing. So we're going to have a bar checking error here, right? Name doesn't work. Expected stir found struct string. Method name stir. Oh. So when we call value, we don't pass in that, we just pass in the arg count, and we rely on this to be the right thing. Okay. All right. Pretty simple fix, it says right there. Pretty simple fix. Once we figured out what we needed to do, let's see if it actually works. Cargo run, oops. Not a method. Okay. So that was a pretty simple fix, and we are still using the invoke. Before looking up a method on the instances class, we look for a field with the same name. If we find a field, then we store it on the stack in place of the receiver under the argument list. Yeah, so it replaces oops instance with a fnf. And last time what it tried to do, it left the oops instance on there, and it couldn't invoke a field because there was no method name field. Okay. This is how opt-get property behaves since the latter instruction executes before a subsequent parenthesized list of arguments has been evaluated. Then we try to call that field's value like the callable that it hopefully is. The call value helper will check the value's type and call it as appropriate or report a runtime error if the field's value isn't a callable type like a closure. All right, we can actually double check that, right? Oops. Right? If I can say this dot foo equals 12 and try to call oops dot foo like that, it should report a runtime error. Yep, can only call functions and classes. Good. I should fix that because we don't want errors when we run our full suite of tests. That's all it takes to make our optimization fully safe. We do sacrifice a little performance, unfortunately, but that's the price you have to pay sometimes. You occasionally get frustrated by optimizations you could do if only the language wouldn't allow some annoying corner case. But as language implementers, we have to play the game we're given. As language designers, our role is very different. If we do control the language itself, we may sometimes choose to restrict or change the language in ways that enable optimizations. Users want expressive languages, but they also want fast implementations. Sometimes it's good language design to sacrifice a little power if you can give them performance in return. Epic says that's pretty spiffy optimization. Correctness only slows things down. Boo correctness. Yay speed. Yeah, we can make this program go really fast if we didn't have to be correct. Right? The code we wrote here follows a typical pattern in optimization. Recognize a common operation or sequence of operations that is performance critical. In this case, it's the method access followed by a call. Add an optimized implementation of that pattern. That's our op-invoke instruction. Guard the optimized code with some conditional logic that validates the pattern actually applies. If it does, stay on the fast path. Otherwise, fall back to a slower but more robust unoptimized behavior. Here, that means checking that we're actually calling a method and not accessing a field. I don't think we're slowing down that much because we're doing this all in Rust. Let's release and see. It was around 8 point something seconds, right? Yeah, 8.4, 8.0, 8.6, so it got up to 8.7, but who knows what OBS has been doing in the background. Let's see if this slows it down significantly. As your language work moves from getting the implementation working at all to getting it to work faster, you will find yourself spending more and more time looking for patterns like this and adding guarded optimizations for them. Full-time BM engineers spend much of their careers in this loop. Oh wow, it is slower. Huh. I didn't think it would add a whole second to the... Okay, well, it's coming back down. But we can stop here for now. With this, Sigh now supports most of the features of an object-oriented programming language and with respectable performance. The hash table lookup to find classes init method is constant time, but still fairly slow. Implement something faster. Write a benchmark and measure the performance difference. I guess the only thing that would be faster is if you put in the class itself. Oops. Do I have class in here? Oh, I'm not in the right. Boy. There we go. Right, because we have these methods. We could just add, in it here. It should be an option RC closure. So if we do compile an init method, we could just shove it there and we wouldn't have to look it up. But we don't have any. Oh, I wonder if that would be worth doing. Let's just commit these changes. And this one's just called optimized invocations. Oops, did I forget something? Git add source. I did commit-m source. Okay, git commit-m 28.5 section. 28.5 optimized invocations. Wow. INVOCATIONS. There we go. I guess that first one was clipping. Yeah. Okay. So that's that. Let's take a look at what would it take actually if we change the class definition to create an option. Oh, I'm almost out of time. Option RC closure. Maybe this would be fun to do for the next one. Pub fun. Oh, it has to be a ref cell, right? Because we need to be able to modify it. Init ref cell new none. Right? Fun set init method. And this would be self name stir. Oh, wouldn't need the name, just value. And we just need it to be a closure actually. Right, and then we just say self init replace, right, with some closure. And then pub fun get init method would be a self, and it would return RC closure, and we would say self option. If self init borrow is none is a none, else self init borrow as ref, right? Unwrap clone. Nope, I got it wrong. Expected option. Expected enum option found struct RC. Oh, some. There. And now in the compiler, we would have to actually check for that, right? When we add a new method. And I think we already have something which checks for init. Oh, it's not in here. It's in the VM, right? Where we get, we look at the method. We do check for init here in the class, and that would change. But when we create the method, right? Op method, op code method, we'd have to look here instead of calling define method. Yeah, right here, we could just check to see is name equal to init. If name is equal to init, what is name? It's a stir, so that works. Then we're going to do the new thing, class.unwrap.setInit method. And method is a value, right? And we want to pass in the closure from it. If let value method closure equals method closure without that part. Otherwise, it's going to be a panic. Closure method should have been a closure. Else do this. Oops. Wow, that built. And then the other place is in init. Instead of calling get class method init, we just say class.get init method. Really? Because that already checks to see if it's an option. Okay. All right, so before we actually build this, before we run it, let's check to see if this goes any faster. Nvim source, no, init call. Let's see how long it takes to run this. Class foo init. It doesn't need to do anything, and then we can just say for var I equals 0, I is less than, let's do 1,000,000. I equals I plus 1. Oh, I have to get the clock. Var start is equal to clock. And then I'm going to just say var f equals foo. And that calls the init method. There's no optimization done here, right? We don't look for invariants and stuff. And then we can just say print clock minus start. And that should give us that. So if I say locks bytecode, nope, target release locks bytecode init call 1.5 seconds. All right, so let's make it 2,000,000. Let's just get it a little bit more time. So that should be about 3 seconds, right? 3.064. And then if I say now build this, does this go any faster? No, it goes slower. Okay, that's sweet. Lover for KTJ, thank you for the follow. Why is this going slower? We're not having to do a lookup in a hash table anymore to do the initialization. That's frustrating, right? I thought that would have done. Well, I thought that would have done the trick. Wow. Okay. I'm sad. Oops. Get in it. Yeah, so this is when we're doing class, we look for the init method. Epic says, happy reverse optimization day. Yeah, so that's twice in a row we've done something that's supposed to be faster and then it makes things slower. So, wonderful. I'm going to throw all these changes out now. I mean, this, right, this should be faster because it's because we're just looking it up. Maybe most of the work is done in here. When we do get method, we call methods borrow get cloned, right? So we're doing this. We're still, maybe most of the work is in the clone. Maybe that's what's happening. And this optimization doesn't really help us. Get method is fast enough. I mean, the hash table lookup is fast enough that this doesn't help us at all. That's terrible. Brooke says, is it only slower in debug mode? No, I'm running everything in release. I'm compiling everything in release. Never test optimizations with debug code. That's a rule I learned many years ago. Always use release. The problem is, of course, I'm running OBS and I'm running Pretzel and my sound stuff, loopback, and all that kind of stuff on here. So this is not the best test environment. So I'm going to keep these changes. Actually, I just changed my mind. I'm going to keep these changes, and then I'm going to test them on a separate machine. Attempt to make init calls faster. And I'm going to call that a stream. There we go. All right. With that, oh, Brooke, I would have gone over to you, but I got to go. So... who else is streaming? Who can we raid? Brooke Zerker says if it's slower now, you may have made it faster before the real bottleneck. Yeah, that's a good point. What I need to do, what I'm going to do actually after the stream is just boot onto a clean environment, and then just try running both versions and see what happens. Let's go over to Jackie codes, and then don't forget. So, Brooke Zerker, are you still setting up the AWS thing? What are you working on? You got any U stuff going on? If so, people go check that out, because that's really interesting stuff Brooke Zerker is working on. But we'll go over to Jackie codes for now and see what she's up to. She's been making a pretty cool game. It's been a lot of fun to watch. All right, with that, I will see you. No Rust today? Okay, fair enough. I will see you tomorrow. Tomorrow we're going to go back to the editor. I kind of left off here. Yeah, we were going to start chapter 5 on the editor and get that going. And then hopefully next week I'm going to, I've been looking at different roguelike stuff that I wanted to get back into and see what we can do there. So that'll be for next week. Tomorrow is the text editor. Pulumi. I haven't heard of Pulumi. Build deploy manager. Okay. Neat. All right. Well, with that, I will see everyone on the next stream, and I hope you have a great day. Take care.